So I want to welcome the class, the intern class. This is the 25th intern class that I've been through. I'm one of the original equipment. And I want to give some contrast to Dr. Hassel's, which was a great lecture, you know, of self-affirming, wellness. I'm not into that. So my job, I'm the research director, and I'm very interested in evidence-based medicine. And my goal is to make you uncomfortable in the clinical area and in lectures. So my goal is to say, what's the evidence for what you're doing? You know, why are you ordering a beta natriuretic peptide on a dialysis patient? Why are you doing that? Why, you know, how many troponins do you really need? How good is the urinalysis? How many white cells to define a urinary tract infection? So I'm here to tell you that most of the evidence that you've read in textbooks and gotten medical school is probably at least outdated and probably wrong, and that we have to go back to the medical literature, and you have to be able to critically review the medical literature. Just because it's published doesn't mean it's true. 90% of the medical literature, I will say, is crap, and you shouldn't follow it. But you're going to have to spend the rest of your career relearning medicine. So, and I'm going to give you the tools to help you relearn medicine and to kind of give a, maybe not a cynical approach, but at least a evidence-based approach. And what does it mean, hypothesis testing? That's what we're going to talk about today. So this is a yeah, none of this. Oh, we're going to put, oh, okay. Yeah, okay. So we're gonna, I followed Jimmy Willis' lecture idea, and we're going to talk about inferential statistics. We're going to talk about the null hypothesis, which is kind of a crazy concept, but we're going to spend most of the lecture talking about it because it is how frequentist statistics, the general statistical tests we use in the medical literature, is based on this crazy idea of the null hypothesis. And I'm going to try to explain it so you understand it, and we'll see if it works again. We're going to talk about type 1 and type 2 errors. We're going to talk about alpha and beta probabilities and p-values. I'm not going to talk about this, choosing the right statistical test. We'll talk about this at a later time. Independent and dependent variables, I'm going to mention them. We're not going to talk about the basic data types. This will be for a future lecture. Parametric and non-parametric, this is just terrifying. We're not going to talk about this. But we are going to talk about clinical significance and statistical significance and what the difference is. So these are the problems I see with statistics. First, doctors, is that all I want to know is the p-value, right? All I want to know is the p-value. You know, you read the abstract, you don't read the paper, you certainly don't read the method section. You're looking for the results for a p-value of less than 0.05, so I could use drug A over drug B, or this, prognostic indicator, or this laboratory test works. I'm just looking for the p-value, which is just wrong. And most physicians, in my experience, hate math. I love math, and but most doctors don't like math, and that's maybe why you went into being a doctor instead of finance. And I think we all believe, this is fallaciously, that statistics should be left to the statisticians. I think we all have to have some basic understanding of statistics to be able to critically review a paper, to see if they use the right statistical test. Again, once the paper is peer-reviewed, you would think that the journals hire statisticians and the peer reviewers are experts in the field, and bad papers don't get through. Bad papers get through all the time, and I think I've published some of them. You could just use a statistical program. Unfortunately, maybe this is good and bad, statistics programs got too easy to use. And basically, anyone now can find a good statistical program and get a p-value. In fact, there are online calculators through the internet for every statistical test you could imagine. And if you have some data, you can put the data in and get a p-value. That's good because we should be able to do that. It's bad because it's too easy, and too easy to use the wrong statistical test and misinterpret the p-value. And this was for medical students, is that all I really want to know about statistics is to get through step 1, but now you're just interested in step 3. So there are 2 types of inferential statistics that I want to talk about today. There's the frequentist approach, which is the basic statistic that you're familiar with. Student t-test, ANOVA, Kruskal-Wallis, Mann-Whitney U, Fisher's exact test. All of these are in the frequentist arena. This is what is being used in medical journals for the last 100 years until now. There's another way of doing inferential statistics, the way I think is the future, called Bayesian statistics. So frequentist statistics was started in the early 1920s in England by a guy named R.A. Fisher. R.A. Fisher, major alcoholic, by the way, major alcoholic. Very much was discredited many times because major publications were to show that smoking doesn't cause cancer. So we have some questions about that. Now, Neiman and Pearson, they came up, so Fisher came up with the idea of p-values, and Neiman and Pearson came up with type 1 and type 2 errors. If you read the history of statistics, which I really enjoy, which is probably the only one in the room, or probably on Zoom, I like to see the history of statistics that Neiman and Pearson, who came up with type 1 and type 2 errors that were related to p-values, Fisher really disliked, and there were tremendous fights in the medical literature between them. For Bayesian statistics is by a guy named Thomas Bayes. Thomas Bayes was one of the first nonconformist ministers in England, died in 1761, and came up with the most important statistical theory. This was about gambling. It had nothing to do with medicine at all. It was 1761. It was really, they were putting leeches and bleeding people. And he had no interest in medical theory at all. This was about gambling. Now, why a nonconformist minister in England in 1761 was dealing with gambling, we don't know. He never told us. But he did come up with the most important theory of statistical analysis that is used today. And it's starting to be used for inferential statistics. There's a difference in the frequentist approach. The frequentist approach determines, it is based on deductive reasoning. So it comes up with a model, the null hypothesis, which we're going to talk about. And the idea is to do a statistical test to test the probability that the null hypothesis is correct. We're going to talk what the null hypothesis is in a minute. In Bayesian statistics, it develops the model from the data. So it uses data from the study and then develops a model and then tests the model. It's different than frequentist statistics. It's the opposite way around. What is tested in frequentist statistics is the null hypothesis. The null hypothesis, again, I'm going to say this once and maybe many times. The null hypothesis is there's no difference between drug A and B. It assumes, before you do the experiment, that there's no difference in A and B. And the data then test the null hypothesis. What's the probability of the null hypothesis being correct given the data? That's how it works. It's not to test which drug is better. It's just to test what's the probability that they're the same. It's not the research question, right? No drug company gives me $1 million to test drug A is equal to drug B. But that's what statistics tests in the frequentist approach. In the Bayesian approach, it tests directly. Is drug B better than drug A? And by how much? And what's the probability that drug A is better than drug B? It tests the research question directly. Where frequentist statistics, that's the one we use, is just about the null hypothesis, that there's no difference. What's the probability that there's no difference between the two groups? The probability estimate, the p-value that you all have seen, is the probability of the null hypothesis being true given the data that you've done in the study. Bayesian statistics predicts the future based on the data that you have. So it says, if drug B decreases the blood pressure by 30 millimeters of mercury, what's the probability in the future, if you give it to a patient, that it'll drop 30 millimeters? That's what you really want. But frequentist statistics doesn't test that. It just tests the null hypothesis. What's the probability that the two drugs are not the same? What's the probability that age is not a prognosis for cancer? What's the probability that an elevated cholesterol predicts coronary artery disease. So they're different, but we're not going to talk about Bayesian statistics anymore because it is not the primary hypothesis testing statistic that's used in the literature. There's a few papers out there, maybe some of mine in the future, but what you will see in the medical literature is the frequentist approach. And that's what I want to spend time on, because I want you to be able to critically review papers and know what they're testing. So what is it? What is the null hypothesis? There is no association between the predictor or independent variables and the outcomes, the dependent variables. So if I'm testing two antihypertensive agents, right, and I want to know which one decreases the blood pressure, the frequentist approach, the null hypothesis, says that there's no difference in the effect on blood pressure between drug A and B. There's no predictive value of cholesterol for coronary artery disease. D-dimer does not help you diagnose patients with COVID-19, right? That's what the null hypothesis says. The null hypothesis, the statistical question that it answers, is the only difference between any of the groups in the study is just by chance. It's just sampling error. And the researcher's goal, and all those statistical tests you've learned that come up with a p-value, just tells the probability of the null hypothesis being correct given the data of the study. That's all it tests. It doesn't, if the p-value is 0.001, it doesn't say that drug B is incredibly better than drug A. It just says that they're not the same. That's all it tests. It doesn't test the research question. It just tests the null hypothesis, which is kind of a crazy idea, but R.A. Fisher is now called. So one way of thinking about this frequentist and a null hypothesis is to compare it to a jury trial. It's not my idea. I stole this from somebody, but this is kind of a way to think about it. So in a jury trial, you start with the presumption of innocence. And in the statistical significance is you start with the presumption that the null hypothesis is true, right? So this is how frequentist statistics works. It says, before I do the study, I assume drug A is no better than drug B. I assume that cholesterol doesn't predict coronary artery disease. That lactate has no effect on telling me the prognosis of a sepsis patient. It just says there's no difference between the two groups. A jury trial listens to the evidence, but screens the jury out, right? The jury cannot look at newspaper articles. They're not supposed to have a biased opinion before they see the data, before they hear the trial, right? They're not even supposed to talk to each other until the trial is over to prevent bias. And in frequentist statistics, that whatever has come before the study cannot affect your idea of how the results of the study. In fact, in frequentist statistics, there's a starting and stopping rule that you cannot even analyze the data until you hit the sample size that you predetermined before the study. And that you can only look at the data once. You can only do the one statistical test that you plan to do, and that's what you get. And the studies that come before the study cannot influence your interpretation of the study at all. You got it? So the jury, once the jury gets, the jury is out and the closing arguments are in, the jury votes on the evidence, guilty or not guilty. And in a statistical test, this is what you do to come up with the p-value. Fisher's exact test, student t-test, Mann-Whitney U, chi-square, Fisher's exact test. This is like the jury voting guilty or not guilty. And then the jury now weighs the strength. How strong was the evidence for guilt or not guilt? And in the statistical, you get a p-value. So the p-value assumes the null hypothesis is correct. And what is the probability of finding the same or greater difference you found after repeated samplings of the data? So it's the probability that the null hypothesis is true. That's all you get with the p-value. A jury does never find innocence. It finds guilt or not guilty, right? There's a difference between not being guilty and innocent. Innocent is a term in the universe or God, whoever you believe in, that you didn't commit the crime, you really didn't commit the crime. But the jury, they don't try to do that, right? They're not looking for truth in the universe. They only are, I was given this evidence, and I decided on the strength of the evidence that the person was guilty or not guilty, right? It doesn't mean that they're innocent if they're not guilty. Trump has confused this many times, right? Many times. But, so there's a difference between guilt and not guilty, right? But if you're not guilty, it doesn't mean you're innocent. It just means that the court failed. Maybe the defense lawyer was poor. Maybe there was bias in the courtroom. For whatever reason, guilt or not guilty. And also in statistical parlance, you could reject or fail to reject the null hypothesis. You can never accept the null hypothesis. You can never say that no matter what I did, drug A is never as good as drug B. There always may be some difference. And we're going to see with the law of large numbers that if you do a large enough sample size in frequentist statistics, and this is a problem, you almost always hit a p-value of 0.05. And that's what we're going to talk about later in the lecture. So so this is guilty or not guilty, accept or fail to reject or fail to reject the null hypothesis. But never accept the null hypothesis. You either reject or fail to reject the null hypothesis. And then how do you do it? There's two different types of jury trials. One is a criminal trial. A criminal trial that the outcome of a criminal trial is you go to jail, or in some states, the state kills you, right? So the bar to say that someone is guilty in a criminal trial requires a 100% consensus of the jury, right? If you ever see the movie 12 Angry Men, a criminal trial, because the outcome is such a dire consequence to the person presumed to the crime, that the bar is set very, very high. The bar is set very, very high to convict. And in statistical significance, we talk about alpha. Alpha is the bar for the p-value, right? The lower the alpha, the actually higher the bar to reject the null hypothesis, right? Because it's the probability that the null hypothesis is true, right? So if you set the alpha very low, 0.0001, right? When you set the alpha very, very low, then the bar is set very, very high to reject the null hypothesis. It's very difficult. You have to have a lot of evidence on the side of rejecting the null hypothesis. You know about physics? You know when they decide on a new particle, like the Higgs boson, do you know what the p-value was? They use frequentist statistics there. You know what the p-value was? It's 1 times 10 to the minus 5th. It's actually 1 with 5 zeros before it, not 0.05. Like we use in medicine, 0.05. We're going to talk about where the 0.05 came from in a minute. But so the physics societies, to accept that that the Higgs boson was real, took a p-value of 1 times 10 to the minus 5th. We use 5 times 10 to the minus 2nd, right? 0.05. So they are 10,000 times more, it's more difficult to define a physics argument than just to give a drug, which is a little disturbing. In a civil trial, you just need a preponderance of evidence, because in a civil trial, the outcome is you have to pay someone some money. The outcome isn't as dire. The outcome isn't as threatening to the plaintiff, right? It's not as dire. So in a civil trial, we can set the p-value much higher and then lower the bar to reject the null hypothesis. A good example of this, let's say you had two drugs, drug A and drug B, And drug B, this is a chemotherapeutic agent. Drug B decreased mortality rate by 2 years for this cancer. Well, that's great. But drug B also has a very high complication rate. Very, very high. 10 times the complication rate. So because the possible harm of the drug is so great and the possible benefit is so great, you would want to set the p-value very, very low and make sure that drug B is really, really changing the mortality rate by 2 years. But because the harm of drug B is very great, I want to really make sure. So I would set the p-value much lower, raising the bar to reject the null hypothesis. Where if you had drug A and B, and drug B looked like it decreased the mortality rate, people live 2 years longer. But now the harm in both drugs was about equal. So if the harm is equal, and one is having such a great benefit, then I would want a p-value would be higher, right? To lower so if I made the p-value from 0.001 to 0.1, right? So it'd be much easier to reject the null hypothesis and accept that drug B was greater. So maybe you should, if you're going to use p-value, you should rejigger the p-value depending upon the outcomes and complications and benefits of the hypothesis you're testing. This doesn't happen, by the way. Everyone got stuck on 0.05. And that's what we're going to talk about in a minute. So alpha is the p-value that we use to reject the null hypothesis. That if the p-value is less than alpha, and alpha is defined by the author in the method section. Usually about the second to last line of the method section, it says alpha set at, and we just use 0.05. And then if the p-value is less than 0.05, we reject the null hypothesis and say that it's statistically significant. So alpha is the p-value that determines statistical significance. And this is set by the authors of the paper. But it's almost never rejiggered for the outcomes or for the complications of the therapy. So where did 0.05, you would think, you would hope that 0.05 had some scientific basis, right? We all would think that R.A. Fisher did some amazing calculus. He was very good with calculus, by the way. Very good when he wasn't drinking heavily. But he was very good with 0.05, and that 0.05 was the standard. It's not true at all. The story goes that there was a party. R.A. Fisher was drinking heavily. His students said, what p-value should we use to reject the null hypothesis? And he just said, oh, just get away from me, just use 0.05. That is the basis for 0.05. A drunken comment by R.A. Fisher. And this comment went through the statistical medical literature and was accepted by the New England Journal. And we live with this every day now. So there is no science behind alpha of 0.05. Nothing. It's just that's what we use. And we got stuck with it. Does that make you feel better? It's supposed to make you uncomfortable. Did I do it? Yeah. Good. So a type 1 error. So this is Pearson and Nyman, who had this big fight with R.A. Fisher, because R.A. Fisher never liked this idea of type 1 errors, because it was based on setting a p-value. And R.A. Fisher, he recanted many times, I'm sorry, I ever said 0.05, I was drinking, I didn't know what I was saying. But Pearson and Nyman said, okay, that there's a type 1 error. A type 1 error is rejecting the null hypothesis is when it's not true. That you find a difference between the two groups that is not really true in the world. And the alpha then, alpha is the probability of the rejecting the null hypothesis you should have accepted, right? So every time you do a p-value, there's a 5% error, because if you use 0.05, that the null hypothesis is really true, because that's the probability of the null hypothesis. So this also goes for 95% confidence intervals. So I like to talk about the labs, right? The labs, you see those stupid parentheses next to every lab. 95%, that's the 95% confidence intervals for that lab. And if the sodium is like 134, it's low, and there's an H, there's a star because we're too stupid to figure out, which ones are low and which ones are high. So there's like a L for low and high for high. Like, how stupid can we be? And the lab calls us that the Miss Cohen's sodium is 134. Thank you. But those confidence intervals are also based on an alpha of 0.05, which has no meaning. So that a type 1 error is where you find the difference between the two groups that really doesn't really exist in the world. And it's a false positive. So this type 1 error is a false positive. So if we use an alpha of 0.05, right, that means there's a 1 in 20 chance that you've committed, even if you accept that the p-value is less than 0.05, there's a 1 in 20 chance that the two drugs are really not different, that they're really the same, or that cholesterol doesn't predict, right, ACS, right? So we accept a 1 in 20 error. And this is important because what we're going to talk about is type 2 errors, that we accept a very different probability for type 2 errors. And this is what we do, 0.05, 1 in 20 chance. And when there's a type 1 error, it's most likely that the study is biased or hasn't been operationalized successfully. There's an error somewhere in the study. Type 1 errors are from bias. Type 2 errors, this is where there really is a difference between the two groups, but the study failed to find it. So there really is drug A or drug B is better than drug B is better than drug A, but the study failed to find it. This is like truth in the universe, right? So, and we use beta as the probability. So the probability of a type 1 error is beta. And when we talk about sample size, which is the error in type 2, when you have a type 2 error in the study, it's most likely because you didn't have a large enough sample size. And we use beta, 1 minus beta, to decide the power of a study, which is the ability not to have a type 2 error. So it finds that there's no significant difference between the groups, but one really exists in the world. And beta, we use, it's a false negative, and beta we use as 0.20, so a 1 in 5 risk. So this kind of makes maybe some sense that we accept a type 2 error at 1 in 20 of 0.05, right? But we accept a type 2 error of 0.2 of 1 in 5, right? Where we accepted 1 in 20 before for a type 1 error. So it kind of makes sense that if you're going to have an error, I would much rather have an error of missing the difference between the two groups than actually finding the difference in the two groups. You see the difference? So a type 2 error we accept as 20% or a 1 in 5, right? But a type 1 error we accept as 1 in 20, right? Because we're much more conservative to find the difference between the two groups than failing to find the difference in the two groups. Makes sense, right? It's about the only thing that makes sense about this. And the problem with type 2 errors is sample size. So a way to think about type 1 and type 2 errors is this box. And this is a good way of thinking about it. At the top of the box, the columns, this is truth in the universe. Now, no one really knows truth in the universe. It's a philosophical concept. And then the rows are the results of the statistical test. So if I accept the null hypothesis, and there really is no difference, well, that's correct. But if I accept there's no difference, and there really is a difference, that's a type 2 error. And then rejecting the null hypothesis when there really is no difference is a type 1 error. So this is kind of a way of thinking about type 1 and type 2 errors. Again, type 1 error, right, is a false positive. There's no difference between the two groups, but because there's some bias in the study, you found difference between the two groups, or you just set the p-value wrong, right? There's some bias in the study. Type 2 error is there really is a difference between the two groups, but you failed to find it because usually the sample size was too small. So putting it all together. So all statistics is based on a random sample. And you have a good paper should state the null hypothesis. A good paper should define a threshold for a statistical analysis. It should just say alpha in it. Now, these are good points in the generally when you're looking at a paper. I spend a lot of time looking at the method section of each paper. Hopefully you will in the future, because just because it's peer reviewed doesn't mean it's a good paper and doesn't mean you should use it to change your practice. And one of the ways to find out is if the paper doesn't say anything about the alpha. If a paper in the method section doesn't say what they set the alpha is, then this is not a good paper. Then maybe you should start to think about rejecting this paper and not changing your practice based on it. So then you do a statistical test, you get a p-value, and if the p-value is less than the alpha that you set, which is usually 0.05, or because R.A. Fisher was drunk one night again, that you can reject the null hypothesis and say there is a difference between the two groups. So I wanted to talk about at the end clinical significance versus statistical significance, and it has to do with the law of large numbers. So why do drug companies spend so much money looking at 10,000 patients? Because they hired the statisticians who knew Frequentist statistics. And if you put enough patients in a study, you're almost always going to hit a p-value of 0.05, because that's how it works. Because little differences in the samples for large numbers almost always hit p-value of 0.05. People have made their whole careers, billion-dollar drugs, 0.04, statistically significant, everyone buys this drug, right? The example of the statins, by the way. This is kind of a crazy idea. But the statins, 0.04, billion-dollar drug, right? Law of large numbers. The other problem is the effect size. Is how big should the difference be between the two groups to be clinically significant? Because I once told you that even small differences in very large sample sizes will hit p-value of 0.05. If you have two drugs, antihypertensive agents, and one drug decreases the blood pressure by 5 millimeters of mercury, the p-value is 0.04. Is that a drug I would give to a patient? A 5 millimeter drop in blood pressure? That's not clinically significant. But because the p-value is less than 0.04, it's statistically significant, right? So this is the difference. You can be statistically significant, but the effect size, the difference in the outcomes of the drugs, or the predictive value of cholesterol for ACS, or the predictive value of the D-dimer for COVID-19, can be 0.04, but what is the number? How big is that number, and is it clinically important? Surrogate outcomes. So a lot of papers, my favorite group of papers, are contrast-induced nephropathy, if you know my interest, is that if you give someone contrast, that in 48 hours, a small number of them bump their creatinine, right? And everyone said, well, that is contrast-induced nephropathy, except that none of those patients go on to need dialysis or renal failure or even have long-term impact. In fact, in 48 hours later, the creatinine comes back to normal, and it had nothing to do with the contrast. So this is because they're looking as a surrogate outcome, creatinine, as for GFR for renal failure. And this is a surrogate outcome, a standard. Utility. So what is the effect of finding out this information from a patient's point of view? I recently reviewed and definitely rejected a paper that looked at diabetic ketoacidosis. And the question is that the paper question was, could I find the results in the initial lab that predicted clearance of DKA in 24 hours? The patients who would clear DKA in 24 hours. And the paper found this amazing fact that the patients who were sicker took a longer time to clear. So the patients who were sicker took a much longer time to clear. Well, I could have known that before. And from a patient's point of view, who cares? They were the ones who were sick or not sick, and they cleared within 24 hours. I also said that you should never publish this paper in emergency medicine, because if the ICU doctors find out, they're just going to delay any admission for DKA patients until we finally clear the patient. And my argument was that, you know, I knew before the study that sicker patients would take a longer time to clear. You know, it's like has there ever been a randomized clinical trial of parachutes, right? So no one has actually, you know, taken a whole bunch of randomly selected people, throw them out of a plane with a parachute, without a parachute, because we know the result. We didn't have to do the study. And we didn't have to do the study to see that sicker patients with DKA took longer times to clear. So utility. And then finally, we're going to talk to questions. This is Ernie. Ernie passed away about a year ago, but he's still with us at the end of every lecture. So if you have questions, I'd be glad to answer the questions. Thank you very much.